So last time we went over the derivatives of our inverse trig functions, and now we're going to end this section by just looking at a few examples. Essentially, we have new derivative rules, and so, we could just work on a couple of derivatives, any of the types of problems that we've worked on up until this point, just using our new derivative rules. So number one, suppose we have g of x equals arctan of 5 over x, and we're asked to find g prime. All right, so the derivative of arctan, if you go back up and take a look at your list up there, you're going to see that your derivative of arctangent is 1 over 1 plus, and now the inside function left alone. So in this case, the inside function, the f of x in this case, is the 5 over x, so that quantity squared, and then by chain rule times the derivative of the inside. Well, if we think of 5 over x as really being like a little 5x to the negative 1 power, so that's kind of my preferred way. I mean, you could leave it like it is and do quotient rule, but I think if you can literally just think of it in your head as 5x to the negative 1, and then your derivative is negative 5x to the negative second, which of course is just negative 5 over x squared. And if you can go there right away, that's even better. So what do we now have? We have 1 over 1 plus 25 over x squared, and then times negative 5 over x squared. Well, multiplying fractions, we just multiply numerators and multiply denominators. So we end up with g prime equaling numerator negative 5, denominator we have to, and kind of like the fact we multiply the x squared through because we get the reduction of the x squared in the second term. So this ends up giving us x squared plus 25. So there is g prime. All right, number two, h of x is equal to x times cosine inverse of e to the 4x. And again, we're looking for the derivative, trying to find h prime. Okay, so what we need to realize here is we do have a product of two functions of x. We have x, and then times this cosine inverse of e to the 4x. So we have a product of two functions of x, so we do need to apply our product rule. So h prime is going to equal, so let's say we start with our first factor left alone, x, and then times the derivative of the second factor. So this is our new derivative rule, derivative of cosine inverse. So the derivative of the co-inverse trig functions are the ones that are the negatives. And so this is our negative 1 divided by the square root of 1 minus, and then inside function left alone. In this case, that's the e to the 4x, and that quantity squared, so that's the derivative of the outside, and then times the derivative of the inside. So the derivative of e to the 4x, well, it kind of has its own inside, which is 4x. Derivative of e to the 4x is e to the 4x times 4. So this whole quantity here represents the derivative of e to the 4x. And then this is all taking place inside the larger parenthesis, that whole thing being the derivative of cosine inverse. All right, so now that's half of my product rule, plus now the second half is the easier half here. So the second function left alone, cosine inverse of e to the 4x, and then times the derivative of x, which of course is just 1. So we'd probably just clean this up a little bit. So h prime is equal to, I'm kind of a fan of putting a positive term first, so I'd probably write my cosine inverse of e to the 4x. I'd probably put that term first. And then minus, in my second term, I have 4x e to the 4x. That's my numerator portion, all divided by the square root of 1 minus e to the powers to powers we multiply, so e to the 8x. Okay, so there would be my derivative. And of course on any of these it could be slopes of tangent lines, equations of tangent lines. anything like that. But we're just kind of working with a couple of the new derivative rules. Okay, last one here, and this one is 2 arc cotangent of y. You know what? I'm going to change this one as I'm sitting here. Let's change this to arc cosecant. We've done a arc tan, and we've done a arc cosecant, or arc cosine rather. So let's do arc cosecant. All right. So 2 arc cosecant of y minus 4 times the cube root of x equals y to the 4th, and we want to find dy dx. Okay, so even though it's not stated in the directions, this is one of those where I hope you recognize that you're going to need to use your rules of implicit differentiation, because this is not solved explicitly for y, and in fact we would not be able to kind of just solve it, you know, explicitly for y with that arc cosecant of y there. So we're going to go ahead and just recognize we are going to be taking the derivative of both sides here with respect to x. So I'll rewrite that cube root as an x to the 1/3. Okay, so again, the co-functions, as I take the derivative of the first term there, 2 gets carried along as a constant multiple. Derivative of the co-functions, those are the ones that are the negative versions. So this is your -1 over, and this one is the y times the square root of y squared minus 1. You just differentiated a y, so you, by implicit differentiation rules, multiply by your factor of dy dx. Okay, minus, bring down the 1/3, so we'd have 4/3. X to the 1/3 minus 3/3 would give you your -2/3, and then equals your 4y cubed, just differentiated a y, so we multiply by our factor of dy dx. Alrighty, so at this point we need to get all of our dy dx terms on one side, and so I'd probably do that by just adding this term over here. So this is really like a -2 over that fraction dy dx. So if we just add this, so add the 2 over y square root y squared minus 1 dy dx. So we're just adding this term here to the other side. So plus 2 over square root y, or over 2 over y square root of y squared minus 1 dy dx. All right, so now on the left-hand side, I just have this x term that's remaining here. So you can leave it as x to the -2/3. If you want to drop it down into the denominator, it would be -4 over 3x to the 2/3 if you bring that into the denominator. And then on the right-hand side, the reason we get all those dy dx terms together on one side is so that we can factor out that dy dx. So we are going to factor out dy dx from both terms there. So factoring that out, in parentheses, that would leave me with the 4y cubed plus the 2 over y square root of y squared minus 1. And then I'd say we're basically there. This is going to look like a doozy of a final answer, but unfortunately, that's just kind of the nature of this particular one. So I'm going to divide by this quantity of 4y cubed plus 2 over, oops, wrote that wrong, y square root y squared minus 1. So dividing both sides by that whole big quantity there. And so essentially this is our final answer. It doesn't look very pretty, does it? But you know, this is what we have here. So our dy dx and our final answer. I mean, the only other thing, if you want to think about you know, getting rid of some of these complex fractions, we could. I could multiply by those, but I'm just going to go ahead and I think just leave this one. It would take quite a bit of simplifying and not really for any real reason. We're not going to be working with it or anything here. So I'm just going to go ahead and leave this one in kind of a really not so pretty form in the final answer here. So this would be our final answer. So there would be our dy dx. Again, it would take a little bit to simplify. I could multiply by those two little denominators to clear the denominators and do some stuff, but we'll just go ahead and leave it there. So those are just a few examples of working with some of those derivatives of your inverse trig functions. So you have all these new rules up here to familiarize yourself with. So those were all the rules that we developed in the last video, and we only proved one. Some of the other ones will follow similarly. And so next time what we're going to get into in section 3.4, a lot of new derivative rules in this section, huh? So in the next section, we're going to look at derivatives of log functions. So that's what we will be getting into next time.